Hello, everyone. Welcome to this fourth ELLIS workshops on COVID-19. ELLIS is the European Laboratory for Learning and Intelligence Systems and is a network of machine learning in Europe. And within ELLIS, there is a health program. Hello, everyone. Welcome to this fourth ELLIS workshops on COVID-19. ELLIS is the ELLIS, as I was saying, is part of is a European network of machine learning, has a health program that activated itself pretty much instantly upon the emergence of the COVID-19 emergency, and we've held 4 workshops to try to focus and catalyze collaboration between medical and biomedical researchers and machine learners. And I'm very pleased that today one of the speakers actually will talk about work that has been catalyzed through these ELLIS workshops. I'm helping chairing this workshop with my 2 colleagues, Günther Klambauer from Universität Linz and Lena Meyerheim from the DKFZ. And we have a fantastic lineup of speakers. As usual, the way these interacts is through a Google form. So if you go to the web page, there is a link to a Google form where you can post your questions, you can specify who the question is for, and the chairs get to see the questions and will select questions at the end of the group presentation. So there's 2 presentations and then there's a space for questions that will be selected by the chairs. If you can't, I mean, sometimes we get more questions that can be asked in a very short time. All questions get then published on the website later on, and so you can check and you can often start communicating with the speaker through that. So now, without further ado, I'm going to pass on the baton to Günther, who's going to chair the first session. Günther.
Yeah, thanks, Guido, for the kind introduction. So we will have a first session on here with 2 speakers, which is Jürgen Schmidhuber and Uri Schalit. Session will, I think, so we call it neural network and causality approaches. And I'm very happy to have these 2 speakers in the session once again. So I will, the first speakers will talk 15 or 10 minutes. And after these 2 speakers, we will allow for the questions, as Guido just explained. Please put your questions online, and maybe we also get some questions from the audience joining via Zoom, and to allow for 1 or 2 questions from there. So our first speaker is Jürgen Schmidhuber. I think he does not need a lot of words. It's, of course, an honor for me to introduce him as a speaker, as he has been shaping the field of machine learning for 30 years now. And his talk is about AI versus COVID-19. So I would hand over to Jürgen, although it's a bit early, 5 minutes earlier that we had planned. Jürgen, are you already online? Otherwise, we can wait a couple of minutes. Okay. So I guess this means it's a short break of a couple of minutes until 1:40 p.m.
So maybe in these minutes we can mention that there will be further COVID workshops. So the next one will be on the 20th of May and will be organized by the other program committee of Bernhard Schölkopf, Oli Stegele, Michaela van der Schaar, and Gunnar Reitsch. And depending on, of course, we need speakers for that, and there will be a call for speakers. So if you want to present some work COVID-related and machine learning, please get in touch with us at the COVID-19 at ELLIS address.
There you go.
Hello.
Hi, Jürgen, you are waiting.
Hello, Jürgen. We have thanks for joining. I already introduced you as our first speaker, so it's an honor for me to hand over to you to give your talk on AI versus COVID.
Thank you very much, Günther. Can you hear me?
Yes. Connection.
And now let me try to share that screen such that we can see something. Can you see my slides now?
Currently not. Yes. Yes, now it's coming up.
Excellent, yes.
Perfect.
Okay, and can you also see me or only the slides now?
Yeah, we can also see you. That's good.
Excellent. Okay. Thank you very much for inviting me for that. And what you see here, that's a cartoon that I made recently for my overview website on AI against COVID. And down there, you have the link if you are interested in that. And just a few days ago, I gave a keynote at the GMIC conference in Beijing, which is huge, which was about this topic. And the organizers tell me that 2 million people have seen that. So I'm not sure whether we can break that record today. I'm just going to condense everything into a few minutes. And if you get bored, you would just switch it off. We already had lots of excellent ELLIS presentations, so I won't say many new things. AI based on neural networks can help to fight COVID in many different ways. And the basic principle is always the same. You use these deep neural networks to learn, to detect patterns in viruses, and the behavior of the virus and the behavior of humans, of patients, of populations, and you would try to predict future events given certain actions that you might execute, and then you act to minimize damage or minimize predicted damage. And one way of doing that, of course, that is maybe the obvious thing, which everybody is doing, has been doing for months now. You can track populations through pattern recognition. And many of you know the peer-to-peer Bluetooth app on your smartphone, which may prevent potentially dangerous contacts. And not so much AI is needed for that. And it becomes more challenging to recognize faces and gaits of people and their contacts in videos. And for that, you can use these deep networks that everybody has been using for 10 years at least now, actually longer than that, but they have really become popular about 10 years ago. And one of the milestones was really what my former postdoc, Dan Girijan, did back then in 2010, 2011, when he created the first deep learning networks that really were able to win pattern recognition competitions. And then he and the team, they won 4 pattern recognition competitions in a row between 2011 and mid-2012. And that stuff can be used for all the population tracking mechanisms that are now widely used, especially in China, but also in Western countries. And then you have the more interesting task, at least in my point of view. You can use deep learning and artificial neural networks to monitor patients and to monitor their heart rates and their cuffs and their biodata, their biosignals in many different ways, and again that can yield approaches to fighting COVID. If you want to get references on that, then just look at my little website, which has a whole list of interesting references. By no means complete, but not so bad. And when Dan Girijan and the team did that stuff 10 years ago or so, computers were still 100 times slower than today. And compute was 100 times more expensive than today, which means that today we can do 100 times as much for the same price. And neural networks can be used to predict outbreaks of diseases or of spreading of the virus in the population, and they can be used to build early warning systems. And there is a COVID-19 forecasting challenge on that. And neural networks can learn to predict future demand for limited resources, such as ventilators and doctors, to optimize the logistics. And you might want to call that predictive maintenance of the population. Predictive maintenance of the population. Yeah, you can sequence virus genomes, and there have been, there was at least one talk about that here at the ELLIS conference, and you can detect their cities of origin because they are mutating all the time, these genomes, and then you can learn the patterns in the mutations and can predict new outbreaks. And you can predict where is this particular type of virus going to emerge again next, and you can act to minimize damage as always. Yeah, lots of stuff can be done. You can use neural networks to analyze X-ray images of lungs and to detect pathologies, and all of that has been done. And it also goes back a long time. Again, Dan Girijan, my brilliant Romanian postdoc here in Switzerland, he was able to win with the team in 2012 for the first time a medical imaging competition, again, at a time when computers were about 100 times more expensive than today, maybe 70 times more expensive than today. So today we can do 70 times as much for the same price. And back then it was new. So back then people used other techniques to scan human tissue for pathologies. In that case, it was about cancer detection. But today, everybody's doing that, and Google and IBM and Siemens and everybody is using that approach to detect pathologies. You can use the same thing for almost any kind of medical imaging. Yeah. What I think is really interesting is that you can use these networks to automate drug design. And the team of Sepp Hochreiter and Günter Klammbauer and the other guys in Linz is really strong at that. And already in 2007, Sepp Hochreiter, my former student, of whom I'm really proud, he had a system that was able to predict the folding of proteins. So you probably know that the virus has a bunch of proteins, not so many. It's a pretty simple virus, and they fold in a certain way. And depending on how these proteins fold, you can figure out where you can dock counter agents on the virus. And that was already done in 2007 when computers were about 1,000 times, almost 1,000 times slower than today. LSTM, long short-term memory, was used back then by Sepp and his team for doing that. And recently, DeepMind also had a system which looked at the sequence genomes of proteins of the virus and used it to predict the folding patterns. And there's a database on that. And maybe you know that the first DeepMinders with publications in artificial intelligence and PhDs in computer science really came here from my lab in Switzerland. So this long short-term memory, which I already mentioned, maybe you already have used it, but probably not for protein folding. You know it from your smartphones. That's where it's doing much of the AI. And if you don't know it, I can't really mention the details of how it works, but at least I can mention the brilliant students and postdocs who made it possible, starting first of all with my former student, Sepp Hochreiter. Already in 1991, he had fundamental insights in his diploma thesis, and then Felix Geers, already in my Swiss lab, who had important contributions, and Alex Graves, who improved it also in many ways, also in terms of the error functions that you use to train the thing. And now it's doing all the speech recognition for Google. Whenever you use your smartphone and you say, okay, Google, what is the shortest way to the station? Then it understands what you're saying and translates that into a query for the search engine. And the same LSTM is also has been used in 2016 to revolutionize translation from one language to another. And soon Facebook was doing that about 30 billion times a week for translating 30 billion messages a week through LSTM like that. And it's really nice to see that stuff like that can also be used to do, for example, natural language processing in the fight against COVID. So there's another Kaggle challenge where the goal is to scan the literature and find from the literature, much of this bulk of literature is kind of almost lost or hidden behind walls in the past, and now how can you data mine all these informations, all the information that is in there to find therapies and better molecules for the fight against COVID. So that's one of the challenges, the Kaggle challenges that is going on. And stuff like natural language processing is really significant there. What I'm most excited about is that you can teach neural networks to become chemists, artificial chemists that learn from lots of examples to figure out how chemistry works. So maybe you have a big database. Bayer is one of the companies that has a huge database of reactions where you get input ingredients and then you get output substances as a consequence given certain conditions such as certain catalyzers, certain temperatures, and so on. And the network learns to model this reaction, and it learns to model many other reactions, and over time it learns to understand and to predict how chemistry works. And then you can take the network and run it backwards, and you can say, let's now have a desired output substance which has properties that we have never seen before in any substance like that. And you can calculate backwards and say, what kind of ingredients do I need given this model of chemistry such that I can cheaply produce such an output substance that has this quality. And this approach has really revolutionized and is currently revolutionizing chemistry, and the jaws of engineers dropped when they saw how greatly the development time for new chemical substances with desired properties and new drugs, how much that can be accelerated. The neural networks in the past already learned to win chemical learned competitions about chemical understanding. The Merck Molecular Activity Challenge was won by the University of Toronto already in 2012. And the team in Linz won the TOX 21, was it called the TOX 21 challenge? Something like that. Was it called the TOX 21? Yeah, I think so. Where the goal was to predict the toxicity of substances, and again, an application where AI and deep learning really can greatly contribute to medicine. Neural networks can design new molecules, or can help to shorten the time needed to design new molecules and to decrease the number of trials that you need to come up with promising candidates. For example, there's a famous paper by Segler and colleagues from 2018. And what you also can do is you can find the antibody needle in an antibody repertoire haystack. And this was again done by the University of Linz in the team of Günter Klambauer and Sepp Hochreiter. And Linz is really strong. They have lots of applications in that domain. So the typical drug discovery pipeline goes like that. You need 6 years or more to select just a few out of 10,000 compounds, chemical compounds, and then you need many years of clinical trials, maybe 7 years of clinical trials, and then you need still 1 or 2 years of approval finally. And this is way too long for this fight against COVID, where we need a fast way of using machine learning for improving the situation. But it is possible to do that, and one can speed the whole process up through virtual screening. What is now really important also in context of this JEDI competition, you take a large chemical database such as the zinc database, and Günther talked about that in a previous ELLIS workshop, I think in the first or the second one. And the zinc database contains about 1 billion descriptions of different molecules. And then you would take a SMILES LSTM, that's what the University of Linz has developed there. And you pipe the data through that SMILES LSTM to suggest about only 30,000 top scoring molecules as SARS-CoV-2 inhibitors. And that works really well. You take just the few suggested things and test those in the wet lab, and you do the assays for that, and that can greatly reduce the time that you need for the drug discovery process. So the JEDI challenge, which started just a few days or weeks ago, I think on 10th of April or something like that, is about that. You can win up to 2 million euros if you have the best performance there. The JEDI initiative calls itself the European Moonshot Factory, and that's one of the first moonshots that they are financing. Well, most of what I've said so far is about supervised learning, imitating nature and chemistry, predicting what patients do or what is going to happen to patients given the data from the patients, and so on. I'm always keen to point out that we also have systems that are not just slavishly imitating teachers, human teachers, but that invent actively their own experiments in an unsupervised fashion, such that they set themselves their own goals to figure out how the world works and what you can do within this world, and how you can solve self-invented problems in this world. And then over time, as the repertoire of solvable problems becomes larger and larger, the system can also, at least in many situations, also speed up the performance when it comes to learning tasks that are given by outside forces, by humans, for example. However, that at the moment is probably too, that's not fast enough for finding a quick solution to the COVID-19 crisis, which needs a fast response. And so I just want to mention that. One final thing, maybe many people are asking, how is COVID-19 going to affect the economy? And I should know, because we have a startup called Nascence, which is affected by that. Nascence is pronounced like nascence, like birth in English, but spelled in a different way, and N for neural networks and AI for artificial intelligence, because it is about the birth of a general purpose AI, which learns through curiosity and other techniques, all the stuff that it doesn't know yet, and then quickly can learn a new thing given what it has learned so far. Now, our clients are affected by the corona crisis. All the major companies in the world are affected. However, as the Chinese know well, every crisis is also an opportunity, and we strongly believe that large parts of the industry are going to emerge in a stronger way out of that crisis. Many industries are currently shocked into digitalization, which on the surface expresses itself through heavy use of things like Zoom and Microsoft Teams and all these things. But on a deeper level, there is now this growing incentive to solve all kinds of problems which needed lots of human work, better and faster and cheaper through smarter and smarter machines of the types that Nascence is producing. Let me finally state that I think that AI is not going to be dominated by a few big companies. No, it's going to be many, many small companies and big companies that are going to profit. And most importantly, it's going to be everybody in the population who is going to profit. AI is for all. It's getting cheaper all the time. Every 5 years, compute is getting 10 times cheaper. So within 30 years, we have a factor of 1 million, and it doesn't look like this trend is going to break. The trend has held since 1941, when Konrad Zuse built the first program control computer, which could compute maybe 1 elementary operation per second, and now 30 years later, you could compute roughly 30, or you could compute 1 million operations per second for the same price. And then shortly after that, 30 years later, you could compute 1 million instructions per second and so on. And today it's about 1 million billion instructions per second. So a large LSTM of today, which has been used for translation, for example, has maybe 1 billion parameters, 1 billion connections. And if you compare that to your own brain has about 1 million billion connections. So it's about a factor million bigger. Nevertheless, a factor of 1 million is just 30 years. And the whole thing is going to become cheap and cheaper and cheaper and cheaper, just like with mobile phones. I remember once I had a rich friend, 40 years ago, I had a rich friend, and he owned a Porsche. And the most exciting thing was that in the Porsche, there was a mobile phone. So he could pick up the phone and he could talk to anybody who also had a Porsche like that. And today, a few decades later, there are billions of people who have mobile phones that are much better than what he had in his Porsche. And they can do much more with their smartphones than he was able to do. And the same is going to happen to AI. Many, many people are going to have many different AIs, making their lives easier and healthier and happier. Let me come to my final slide, which is not so much about technology, but more about the geopolitics of the coronavirus. 100 years ago, the Spanish flu emerged, not from Spain, but from North America, apparently from Kansas. And more recently, the Chinese flu, the coronavirus emerged apparently from Wuhan. And if we look further back in history, we'll find many cases where the rise and the fall of empires went hand in hand with viruses and germs and diseases. And maybe the most extreme example of them all is not the current one, and it's not the Spanish flu of 100 years ago. No, maybe the most extreme example is the one that happened 500 years ago, when the Europeans discovered or rediscovered and then invaded the Americas. And back then, there existed only about 500 million people on this planet, 500 million. And 60 million of them lived in the Americas. And apparently almost all of them, 56 million of them, died through the diseases which the Europeans brought, the germs and the viruses that they brought, against which they had no resistance. That was maybe the most extreme case of unconscious biological warfare ever. If you scale it up to the current population numbers, then this would be equivalent to the death of 1 billion different people. So in many ways, the current situation is far less extreme than it used to be back then. And I think what we have seen at this workshop in many talks is that there are many ways of using deep neural networks and artificial intelligence to improve the situation against COVID. If you want to see more, please have a look at my little web pages. And for now, I'm thanking you for your patience.
Thanks, Jürgen. Thanks for the great talk. We're of course happy to have you here, and maybe you could stay a couple of more minutes because after the next talk, there would be a couple of questions addressed. Okay. So let's move over to our second speaker, Uri Shadid, and he's assistant professor at Israel Institute of Technology, and he was before in the US. He's going to talk about extreme domain adaptation, an early COVID-19 risk score, and he's also advisor for the government of Israel. So Uri, I would hand over to you.
Thank you. Can everybody hear me?
Yes.
Okay. So I can't share screen yet. Oh, now I can. Okay, can you see the slides also?
Yes.
Awesome.
Yes.
Thank you. So I will talk about a very specific project which we did, which I think highlights how machine learning, like a specific example of how machine learning was impactful here in Israel in dealing with the crisis. And I will end the presentation with a small request for collaboration, which I hope might come up from people listening. So this came out from work with one of my research partners who are called Clalit Health. It's the biggest health provider in Israel for 4.5 million people. And they have both, they're responsible for patient care in the community and in hospitals. So it's the entire journey of the patient. And they have a lot of data going back 15 years. And because of that, and because of my interest in using machine learning in healthcare, we've been collaborating with before the pandemic for the last 2 years, and we have a very good relationship. And I know their data, and you know we've been working together. So in early March, the pandemic was obviously already coming, and Clalit wanted to build a risk score. So this is a very standard task, right? And in general, you just build some prediction model to predict, for example, if a patient is infected, what's the risk of dying? The problem, of course, that this is a new pandemic, and that makes it hard. So specifically, they want to know for every individual who's susceptible to infection, which is basically maybe everyone, what is the risk of them dying if they're infected? And why do they want that? Because they want, for example, to contact people who are at higher risk and tell them stay at home. And now everyone went through lockdown, but early March, it was still not obvious where this was going. Prioritize testing to people more at risk. And even help decide who should we hospitalize, because we know that many patients do not suffer any serious disease, and we knew that even back in early March. But if someone is at higher risk, maybe we want to send them to the hospital, even if they're currently in a mild condition. So for all that, we wanted the risk score, which is, again, very standard in healthcare. But what data did we have back in early March? So back then, and even now, there's not much public data, and there were no models from any other country. In Israel, where we had access to data because we're the health provider, or I'm working with the health provider, there were only 100 patients back then, and they were mostly young and in mild condition. The early patients in Israel were people traveling in Europe and coming back, generally healthy and younger people. So we couldn't use their data to see who is at risk of dying. We had data from China, but it was only univariate marginal. So China, as far as I know, hasn't released any data set, but they did have tables, like a table like this from the Chinese CDC, which, for example, says for every age group, how many cases, how many deaths, so you could just calculate what's the risk of dying, conditioned on being in an age group. And also you could do it conditioned on being male or female, and on certain comorbidities like diabetes or heart disease, but this is all separate. So these are all univariate marginals, no joint model, no multivariate risk factors. So we don't know if there's any intersections or interactions between the different factors that we can see. And that was back then basically the only data we had for corona. So what we want is a model which I denote the following: P corona, so under corona, the probability of death, conditioned on some set of variables which define a patient, which could be very high dimensional because Clalit has very detailed information. So your entire medical history and demographics and so on. And of course, in Israel, because maybe the disease is different in Israel than in China. We still don't know for sure how it changes. But what we have was just these univariates of P corona of death condition on a specific thing, age or sex or comorbidities, and from our perspective, the wrong country, from China. And of course, over a much smaller set of features than what we have in our data set about the Israeli population. And so no model and data from the wrong country, but still we want to try getting from what we have to what we want. And we came up with an emergency time solution, which involved 3 steps of how to get from that very poor and how would I say, sparse data to a full model. The first idea was, let's build a model for a different disease, the flu. So I think by now everyone knows that this is not the flu, and corona is of course much riskier than the flu. But we have data for flu complications. And our idea was that this would at least help us rank people in a somewhat more sensible way. If you're in more risk to get complications or even die from the flu, possibly you're at more risk to die from corona. It seems like not a terrible assumption, and we validated that with clinical expert, which kind of shrugged and said, yeah, that's probably true. So we could build that data model very well because there are millions of people in the data set, and flu has been going on for years in Israel. So that could be easily done. But that's not the model we need. We need the corona model. So our next step was we could lift, and I will elaborate about each one of these steps. So lift these univariate marginals from China into some multivariate, still low dimensional, but multivariate model. So how can we take all these univariates and turn them into a multivariate model from China? And finally, we want to kind of nudge the flu model from Israel to look like the corona model from China. So we somehow have to recalibrate the flu model to basically say, look, corona is riskier, It's especially riskier for this subpopulation and that subpopulation, which is what we might see from China, and somehow end up with a model which we hoped would be usable. And this all relies on some hopeful assumptions, whereas death is independent of the features we have from China, condition on countries. So, for example, given your age, sex, and comorbidities, a Chinese person, an Israeli person are in the same risk of death. That is still probably not right, but we hope it's not too wrong. Okay, so how do we approach each of these 3 steps? So the first, this is easy, I won't go into this, is standard supervised learning. My colleagues from Clalit, they used XGBoost for this, and train, test, validation, the usual things. The second step, how do we take univariate marginals and make them into a multivariate model? So this is in general impossible unless you make some strong assumptions, which is what we did. So we assume the feature vectors are all binary. So whether you're in an age group or have a comorbidity or not. And here we made a weird assumption, which is we assume that the probability of dying condition on all these things in China is a linear function of X. So a linear probability model. Sometimes people in econ use that. Of course, that might give you negative probabilities or probabilities which are greater than 1. But we needed some assumption that will enable us to do what I will show next. So how is this assumption useful? So we'll denote by mu the univariate vectors of risk of death from corona condition on a specific variable. And we'll have a matrix Mij, which is the conditionals of xj equals 1, condition on xi equals 1 in China. For example, the chance that if you're 30, you will have diabetes, or the age and sex conditional distribution. So how many 70-year-old females are there in China? If you have this, then from the linear model assumption, you have the equation m times w equals mu. And recall that w is the feature vector, the weight vector that we want. So we can just solve for this, and we can take the pseudo inverse and just obtain some w tilde, which is hopefully close to the true w, which again is based on this somewhat unusual assumption of a linear probability model. So this will give us a very approximate multivariate China model of the risk of death condition on the entire vector x1 through xt, w tilde transpose times x. So again, we can lift the univariate to a multivariate using this linear probability model assumption. And this required us to get this matrix M from China, and some of our students were just up all night basically looking up data from China and from papers trying to get these conditionals from China. And of course, we also have this matrix from Israel, which we can use in our data set. So this is the second step, linear probability model assumption. The third step was how to kind of change the problem, fix the flu model to look more like the Chinese corona model. And to do that, we used a very interesting paper from Hebert Johnson et al. It was in ICML 2018. It's called Multi-Calibration, Calibration for the Computationally Identifiable Masses. And I will not have time to go into all the details. I encourage you to look at the paper if you're interested. But it has this definition that a classifier p hat of x is multi-accurate over some family of sets, which might be intersecting. So all the sets S and C, if the expected probabilities over these sets are the same. This is basically motivated, or at least one of the motivations was in fairness, for example. You want to ensure that your expected probability of accepting a woman from Canada into some program is what it should be. And these groups could be intersecting. So that was kind of the motivation of that paper. And they showed that this is actually possible. You could achieve multi-accuracy under some conditions on the set of sets that you want to be accurate on. So that was their main theoretical result. And the way the algorithm does this is you just change probability. So you go individual one by one, and you just change their individuals, nudge them, and surprisingly enough, this converges in polynomial time. So this works under certain assumptions. So this is the result from their ICML paper. And we just repurposed that. And we said, okay, we now want to nudge our flu model to look like the multivariate model we extracted from China. So we're going to recalibrate this flu model to look like the corona model. And we did it over low dimensional marginals such as age, cross sex, and so on. And in practice, we only did this for two-dimensional pairs for all kinds of reasons. We found we couldn't trust higher dimensional things in this model. So bringing it all together, we built a flu model, so a model for the wrong disease. Then we kind of extracted an approximate multivariate model from the Chinese data and recalibrated using this method from Heber-Johnson et al., recalibrated the Chinese model to look to, the Israeli flu model to kind of match the Chinese model, specifically noting the much higher risk of death from corona compared with flu, but also who exactly is at more risk, relatively speaking. Okay, so this gives us some model peak corona of death in Israel, which is what we wanted to use. Now, we made a lot of flimsy assumptions along the way. So, that flu complications could be even recalibrated to simulate corona deaths. China and Israel, we had this hopeful assumption, which might not be true. We used a linear probability model, which is pretty weird. Multi-calibration, that this Hebert and Johnson paper assumes that underlying P of X does not change, so we could kind of fix it, but not really. I don't want to go into the details. So this was very risky, speaking as someone who's developing now a method. We made a lot of bad assumptions. So what did we do to kind of gain trust and say, okay, we can go ahead and deploy this model? First, we only used it for ranking. We said we can't trust the true probabilities. The numbers just, there's no reason they will be calibrated. So it's only who's at higher risk and who's at lower risk. And also, we just devised a long series of sanity tests. We say, okay, we could not deploy this before clinical experts examine the prediction on subgroups. Let's look at descriptives of all kinds of who are the highest risk people, who are the lowest risk people. How does this model differ from the flu model? So we just kind of try to kind of prod this model and kind of stick our fingers in all kinds of places to see whether it makes sense, because we had no test set. We had no way to know whether we're right or wrong. So that was our way to kind of gain confidence in this model. Overall, this entire thing took 7 days from the day we started until it was actually deployed to physicians in the field. So these are thousands or tens of thousands of physicians, thousands of clinics, millions of patients in Israel. This, of course, was a feat mostly of the IT in Clalit of just deploying such a model. Anyone who worked in such things knows how difficult it is to deploy a model. And it was used extensively. They called the patients, they prioritized testing, deciding who to hospitalize. It was used all around in Clalit, this model. What we found, so, and now I want to just say a few things about deploying a model in the real world. It was very hard to change once deployed because we had more ideas. We said, okay, we can make this better. We had 7 days. Once the model was deployed, it was very hard to change. The doctors knew who their patients was. I know, this woman who I know personally is high risk. How can you change her risk now that you've updated your model because you had a better idea? So it was very hard to change once deployed, and that was, for me, an important lesson. There was need for interpretability, which we didn't really have in this first iteration. There was like, if a doctor is calling a patient and telling her or him, you should stay at home, you're at high risk, they want to know why, and we couldn't really give them a good reason in that initial model. Since then, time has passed, and we can actually validate the model because now we have corona patients in Israel. Some of them have regrettably died. So we can now, in the benefit of hindsight, know how well we did. And what we found is using 3,000 Israeli patients, our AUC was 0.94, which is, I think, very high. So we could rank the risk pretty well. And actually training a corona model directly on these 3,000 patients doesn't give a better result. And so surprisingly, this did pretty well. We could, in this figure we show, I compare with some decision rule about who's at risk from the CDC, which was quite useless. Basically said 40% of people are high risk. And just some overall lessons. So desperate times led to some desperate measures. We focused on ranking and on sanity checks because we had no test sets and because the stakes were so high. I don't think I ever worked on a model which impacted so many people. The model was immediately widely used and trusted. So doctors in the field, they told them, you know, the expert gave you a model, they just took it. They didn't ask why and how, and didn't ask what is the ICML 2018 paper relevant or not. I would be less trusting of this model than the people in the field from the reports we've got. And that is actually a source of concern for me, that they just took it up. It places more responsibility on our side to communicate the issues. The model was hard to change once deployed. In hindsight, it was fairly accurate. But I cannot in good conscience say that we knew the risk we were taking, because in hindsight it was fine, but maybe one of those assumptions we made was terrible. And maybe we would have made big mistakes. We tried to avoid them. And I have no kind of solution for this. I'm just saying I'm not entirely comfortable with what we did. We took a big risk. Okay. So just current work. So that's about this work with Clalit. They have now moved on and have better models for many reasons. They know how to do this work. I'm now working with other data sets from Israeli hospitals, very detailed patient data sets. We're working on multi-state models. And if anyone here who is listening is working on patient data anywhere in the world, I would love to talk to them about the possibility of sharing data or models, because I think that could be really helpful. And we haven't seen much sharing going on so far. So that's offline. And just to wrap up, this project was led in the Clalit Research Institute by Noam Barda and Noah Dagan. I have a typo here, that's Noah. The extreme domain adaptation component of this was led by two PhD students, Daniel Greenfeld from Technion and Galiona from Weizmann. And many, many people worked day and night to make this happen. This was really a big, big team effort on lots of sides. Mostly in Clalit, they had to do all the deployment work. And the paper is available on medRxiv. And that's it. Thank you very much for your time.
Thanks, Uli. It was really amazing to hear what you about the impact of your model. So I'm sorry, we are a bit behind schedule. So I would have only one question for Jürgen and one question for Yuri, if this is okay. So Jürgen, if you're still here, somebody in the chat asks if you could give a guess how many years it will take until machine learning is used really to monitor patients in public hospitals, and what do you think could be obstacles and so on. So I think, Jürgen, are you still here? Ah, yeah, okay, great. You're muted. Can you unmute?
Is it going to take until deep learning is used in a routine way in hospitals to monitor patients? That's a good question, and it's probably not exactly my area of expertise, because I'm a machine learning guy and I don't know so much the politics of hospitals. We know that many companies in the healthcare field, such as Siemens and Healthineers and IBM and so on, they are using deep learning to improve the machines that are detecting pathologies in the tissue. And this has happened for many years now. And I think even maybe 5 years ago or so, IBM bought a bunch of companies for $4 billion or something like that, $4 billion. And the only asset of the companies was data, medical data labeled by doctors, such that they could train their staff to better diagnose the images generated by the medical imaging devices. but when is it going to be used in a routine fashion in every hospital? I think it will be the 2nd of February 2026.
Thanks, Jürgen. But I think you're the right person because you have the whole perspective also. So guesses by you are always, of course, better than most of the people, because you're also watching the progression of computers and AI methods, neural networks for a long time. Okay, I would like to move on to a question for Yuri. And so one question in the chat is, do you think the model can be recalibrated online while more data arrives? So I think this a bit is aside, keeping the problems with the medical doctors aside, but just on from the methodological view, I think the question is posed.
Yes, so the model was actually recalibrated and eventually refitted using Israeli data and other data, as far as I know. At some point, I left because kind of they didn't need me and I was more needed more somewhere else. They have a public model now, which is just a points model, like a very simple thing. Just the need for interpretability is so great here. So I think they have kind of fine-tuned models that they use internally, and a public model which everyone in Israel can just look at and add up their points and see how much they're at risk. And they are recalibrating it. So I said it was very hard to change the model. At some point, of course, they did manage to change the model.
Okay. So there are, for all of the speakers, there are a number of more questions. I'm sorry that we cannot address them. I thank Jürgen and Uri again for giving these great talks. And I would hand over to Lena Meyer-Hein for chairing the second session. Thank you all.
Thank you.
Yes, good morning or good afternoon, everyone. I'm Lena Meyer-Hein, and I welcome you to the session Biomolecular Structures. Our first speaker is John Jumper. He's actually a trained physicist. He joined DeepMind in 2018 and is currently the lead for protein modeling. Today, he will talk about computational predictions of protein structures associated with COVID-19. So John, the stage is yours.
Thank you so much. Really excited to be here and talk about the work we've been doing. Oh my, I apologize if I've got some kids in the background. So let me go ahead and present the talk. There we go. And can you all see that? So this is representing joint work by a team at DeepMind that has been working on protein structure prediction for a long time, and then trying to find a good way to contribute to work against COVID-19. And so especially want to call out Catherine and Pushmeet and Demis have really been heavily involved in making sure that we can, someone can only see half the slide.
Yeah, that's true.
Which half?
The left.
Okay. Let's, can you see the whole slide now?
No.
No, but we did when you practiced before. So maybe go back and forth again.
Go ahead. Go the next slide.
Okay.
Are you using multiple screens?
No, just my laptop. Okay, let me switch my sharing mode. Share screen, application window.
Yeah.
Any better yet?
Yeah, much better.
Okay. Great. So this is, let's see, where was it? Oh yeah. This is, so ongoing work we've been doing in structure prediction for a while now, and trying to find the right application related to SARS-CoV-2 and COVID-19. So I'll start with a bit of a non-technical introduction to the protein folding problem, what we're trying to understand, maybe what we can't understand with these types of methods. We'll talk about some of the predictions that we've made we've talked about what are the important proteins in SARS-CoV-2, and our predictions on them and talk about conclusions, future work either by us or places where we think really the community can get involved strongly. And so the proteins themselves are important machines, normally I would say in the cell, but in this case also in the virus, that the genetics of an organism codes for a large number of proteins that perform an enormous number of processes essential to life. And what's really, really remarkable about these machines is that they are produced in a long rope, a single one-dimensional strand or sequence of letters, and then will spontaneously assemble, especially in the small cases, into active 3D structures. And one of the grand challenges in biology is to predict from something that is very, very readily obtainable, the genetic sequence, in which we have many, many genetic sequences of many organisms and of SARS-CoV-2 almost immediately. How can we predict the important protein structures and then use this information to reason about function, misfunction, mutation, etc. And so the kind of machine learning is a sequence-to-sequence problem you can imagine, where you have a sequence over a 20-letter alphabet on the left, and you have a set of 3D coordinates, and we're actually predicting a static shape kind of rather than the dynamical process we're showing. And the challenge of doing this experimentally is the timescales of experimental structure determination are normally in the months to years. There were a few SARS-CoV-2 structures that have come out related to the spike, related to the main protease that came out very, very quickly. But often that's because the proteins that they're characterizing there are extremely similar to proteins that have been crystallized before. And so they're able to reuse a lot of the knowledge on that. And in DeepMind, we focused on what's called the free modeling or de novo structure prediction problem, where we're really trying to understand and predict the structure of proteins for which no similar protein has been crystallized. And what can we do in cases where there's really very, very little information to go off of or copy from, etc. And when you think about SARS-CoV-2, you've got, there are a few different counts, but 27, 29 proteins in SARS-CoV-2, and only a very small number of them are actually part of the virus particles themselves. So you'll see the famous spike protein is there, the E protein and the M protein are also proteins that are structural, that are in the outer, in the membrane of the virus in this case, and inside the virus is the RNA genome that codes for a lot more proteins that are what are called non-structural proteins. So these are proteins that are only really expressed when the cell is infected, that use the host machinery to get produced. And then those are used for the virus to replicate itself and to make new viral particles, and those particles go on to continue the infection. And so in many cases, those proteins are relatively understudied, not all of them. But there are about, say, 10 proteins that really have no known structure. They're often thought to be structured, and we really don't understand a lot about them. And we hope to find ways that we could contribute by making structure predictions about these proteins. And when we want these structures, we want them for a couple of purposes. And we should say, like, the best purpose, the one you would really, really hope, is that if you had the structure of the protein, maybe you could recognize a drug that's already proven safe in humans that could be used for this. It hasn't happened on these proteins yet. It's a very hard thing to do. But even beyond that, there's quite a lot of work to understand the biology of this virus, to understand how it interacts with the host proteins, and kind of get functional hypotheses about places we can intervene. And here, when you're talking about planning experiments or trying to find the meaningful subunits of these proteins that could have individual functions, the individual domains, here really having a first look at the structure can do a lot to help with that planning and understanding of the interactions, and possibly provide context for all the great genetics work that's been going on. So this was a recent paper out of, I believe, Arizona State University, where they looked at a new mutation in ORF7, and that there was a large deleted section of this protein you can see in the top sequence, and they don't know what implications that might have. Or similarly, if you compare to BAT or the original SARS sequence, you can see some variations, and we'd like to understand what those variations might mean. And we can do a lot from a genetics point of view, but we can also give these a structural physical context. Are these surface mutations? Are they deeply buried? Is it on the part that binds one of the host proteins and maybe affects the binding strength? And so we hope that by contributing some structural knowledge, we can start to understand these mutations, put them in context, and contribute to the overall understanding of the virus and the infection process. We should say that this is not just DeepMind that's been working on this problem. So CASP is the critical assessment of structure prediction, is a forum for people to compare their structure prediction methods in a blind competition, and also runs CASP Commons, which folds proteins of interest to the community outside the competition setting. And so for a set of these 10 very hard SARS-CoV-2 targets, 1,600 models were submitted by 52 groups. And you can see some of the structure and meta-analysis starting to emerge, and we've contributed our predictions to that effort as well. And so when you think about protein structure prediction, and this is a field that has developed over many decades, but the very, very high level block diagram is you start from a protein sequence that is obtainable from genetics. And then the very first step is to find all these related proteins in a protein database to find a picture of the genetics and the genetic history of this protein. And that turns out to have, has been shown by many people to have a very, very strong relationship to the 3D structure, that you can predict that thing that even if the positions in a protein sequence are distant, if they strongly evolve together, then that needs some explanation. That explanation is often physical proximity in the folded structure. And so, but it is a very complex and nonlinear function to learn. And so you take the protein sequence, you grab a large collection of related sequences, you go through a whole bunch of machine learning algorithms that I'm not going to go into in this talk. And at the end, you've got a prediction of the 3D structure. And you can see a description of the system that we used previously. We used a improved version for these predictions, but we have a recent paper on this. And so when you apply this system to SARS-CoV-2, we found 6 of the 10 targets we really had a confident prediction on. Some of the other 4 were quite small and may not be structured, or simply we wanted to add to the conversation and not too much noise about it. So when we were not confident, we erred toward holding back. And so you can start to get a picture of these proteins, and you can see the membrane protein, which is structural, but then a lot of the other non-structural proteins, some of which have unknown function, some of which have known function in the viral life cycle. And so we are understanding, we've released these freely. You can see a link at the bottom on where to download these structures. But we're hoping that this gives insights and planning into people on how they do experiments on these targets. One example of this is the M protein. Now, I should say that this is believed to be, if I recall correctly, a tetramer or dimer of dimers in there. So we've only modeled one of the units. But you will see 3 distinct helices that are the transmembrane domain, expected to be 3-pass transmembrane segments, and then the, I believe, intracellular domain. And so this already is something that you can use to provide structural context, to ask where these mutations lie relative to these different domains. We do also, and I would say it's very important in these because these are hard protein folding targets, that we provide measures of confidence on regions where you should trust us and regions where you should really not trust us. And we also interestingly confirm hypothesized similarity to ORF3A, that our predictions for the ORF3A protein and the M protein are very similarly structurally, and that was thought to be the case. Now, in terms of what we think we've done is we think that we've made some contribution to understanding the virus and its mutations, and we make these freely available, and we hope people will build on them. Hope they will build on them in terms of analyzing and understanding the disease, and we hope that they'll build on them in terms of modeling. So some of the questions that are not answered here is, what about all the interactions with the host proteins? In many cases, the experimental methods are starting to show which host proteins are interacted with, at least in a relatively high throughput manner, but we don't know the structure, we don't know the context or the function of those interactions. And so we hope that structural models will contribute to this. I should say on a cautionary note that it will be a very bad sign if drug development really has to proceed against these targets. These are internal targets. They're not very good from an antibody point of view. That's one of the reasons the antibody is focused on the spike, is it's available and accessible rather than being inside the host cell. And there are drugs against the protease, but to develop a drug against a new target like one of these would take years. And so we really hope that current therapy efforts will succeed, but obviously that's something that we're thinking about. And we really hope that they will contribute to our understanding that there's a tremendous amount of structural biology work that still needs to be done against these proteins. We still need to understand how to intervene. And even when we understand a decent amount about the function, rational intervention is very hard. I think there are lots of really interesting discussions about pain medications and their effect on ACE2 and their effect on the virus. And all of this is challenging both biologically and structurally. And so that's what I have.
Many thanks, John. We will take questions after the next talk. So can I remind the audience that you please pose your questions online as usual. So the next speaker is Toby Gibson. He's a team leader at Amble. His team works on biological sequence analysis, and he told me explicitly that he will not talk about AI today, but maybe he will inspire some of you to do AI-related COVID research. Welcome, Toby.
Thank you very much. So I'm going to try and get my screen share working, and then start my presentation. So can you see that, Lena?
Yes.
Great. Okay, so I'm going to talk about short linear motifs, which are of protein structure to what has just been explained, and particularly the ones that we can see in the ACE2 cytosolic tail. I'm going to need to explain what short linear motifs are first. And I've got a subtitle here: if SARS-2 is hijacking our cell networks, how shall we punish it? Because I'm hoping that we can get insights into perhaps drug repurposing. So we started to look at the entry system of SARS once we were all sent home to our houses in lockdown. And so this is primarily my team members' project, with the addition of Friedrich Rittmann from Merck in Darmstadt and Lucia Chavez, a collaborator in Buenos Aires in Argentina. And as I say, there'll be no artificial intelligence in here. You can think about how you might want to apply it, though, to the situations. So what is a short linear motif? So Tim Hunt, 30 years ago, started to see them in cell cycle proteins and defined them as these motifs are linear in the sense that three-dimensional organization is not required. So they're such short pieces of sequence, they don't fold by themselves. The information content is extremely sparse in the sequences, and that means it's hard for us to predict them bioinformatically. So when we're looking at protein sequences and we think we might have found a candidate motif, we ask, firstly, is it conserved in other species? And then we want to know the protein that the motif is in, and the motif is probably going to bind to another protein. So is that activity going to happen in the appropriate cell compartment? So is the protein of interest in the right cell compartment to have that motif? Then we're very keen on getting proximity data, which is coming increasingly, but in interaction networks or in macromolecular complexes. So this is sort of contextual information that we'd like to have to get us interested in candidate motifs. So I'll introduce the motifs from the P53 protein known as the genome, and structured protein sequence in its N-terminus. I've just been told that I've had an unstable connection, so I don't know if anything got lost here. And there's a folded DNA binding domain. I'm pointing to the representation of the sequence at the bottom, and the DNA binding domain can bind DNA. And in the C-terminus of P53, there's another 100 amino acids of natively disordered structure. I hope you can hear me still. And then we have structures that have been solved of various parts. And so we have these little patches of sequence which are binding to other proteins. And in the C-terminus, you can see that actually the same region is binding to different proteins. Obviously, this means that this is a molecular switch because you can't bind to all of them at once. So having these short, accessible pieces of sequence enables far more interactions of proteins than if they were all fully folded up. So someone should speak if I'm being lost.
This is perfect. So
okay, great. Yeah. Okay, so here's the p53 interaction furball. All of these blobs are individual proteins supposed to be interacting with p53, shown in the center. And while the experimental quality may vary, the fact that so many proteins are considered to interact with it gives some idea of the complexity that we're dealing with in cell regulatory systems. And this couldn't happen if it was a fully folded protein. Okay, so we've known for really quite a few decades now that viruses are using short motifs to hijack cell regulation. Norman Davey, Gilles Trava, and I reviewed this in nearly 10 years ago. And we, in our resource, the ELM resource for linear motifs, about a third of the motif classes are known to have viral examples. So the motifs actually be in the viral proteins. And we have a series of structures, representative structures shown up in the right side, where the small red part is the viral protein, the part of the viral protein binding to a host. So there always seems to be a cellular protein motif which the virus can mimic and hijack. And that's clearly indicative of the fundamental nature of the cell, that these motifs are so abundant and so much of cell signaling and cell regulation and control of cell state is going through them that viruses can repurpose them for their own ends. Okay, I should quickly mention the SARS-2 life cycle, because the actual protein we're going to focus on is ACE2, which is the host receptor, or the main host receptor for SARS coronaviruses. It's showing here just one ACE2 receptor, but in reality, the many spikes can bind to multiple ACE2 receptors, and each spike can bind to 3 ACE2s. So a process called receptor-mediated endocytosis is initiated by cell surface receptors. The cell surface of our cells are continually resampling and bringing in vesicles. So the virus comes in, gets uncoated, then you have the whole process of it going out. Oops, I'm sorry, I've gone backwards. But we're going to focus now on the ACE2 receptor. I should just say that this is a very simple, oversimplified diagram of vesicle trafficking. And vesicle trafficking systems take very extensive advantage of short linear motifs. So these are ones that are working on different parts of these systems. And remember that the virus comes in through the endocytic system. Right, so we know that most of the ACE2 sequence is folded. I'm not showing the structure here, but the structure has already been solved. The extracellular domains are highly folded. So this plot here is from the IUPRED server, which is assessing whether the sequences are likely to be structured or unstructured. So the midpoint of the score, below the midpoint is more likely to be folded, and above the midpoint is more likely to be unfolded. So the little tail at the end of the sequence, this is inside the cell, because this part here, which is showing a very strong designed to be folded is actually the transmembrane helix, separating their extracellular domains and the short tail. So the tail is predicted to be intrinsically disordered, and it's fairly likely that it is. So we can put just that sequence of the transmembrane helix, which is all hydrophobic residues, and the tail inside the cell, into our server. We're interested in the fact that the motif should be in the cytosol, so we select that cell compartment, and we want to have the right species, which happens to be Homo sapiens in this case. And then we can set off a search, and it will return a diagram like this. It will give us the IUPRED prediction back, and it will give us matches to regular expressions, so text regular expressions. So we have a very simple system for scoring motifs. And as soon as I saw this, I was very interested, because I know that that's a relevant motif, that's a relevant motif, that's a relevant motif. The one I've highlighted, the PTB-APO, is a relevant motif, the SH2-NCK is a relevant motif, and the endocytic target motif. All of these would be interesting candidates. So one thing we went and did is to check in the largest phosphorylation database, Phosphocyte Plus, for evidence of phosphorylation of amino acids. And the most phosphorylated amino acid in ACE2 is this tyrosine residue Y with 13 phosphorylations. These have all come from high throughput phosphoproteomics experiments. So no one has done any low throughput. In other words, no one has done targeted experiments on this tyrosine, but it occasionally appears in data sets of phosphoproteins. And you can see that if we look at across the whole sequence, there are examples of individual reported phosphorylations which are actually in the wrong cell compartment, and this is probably noise. But the strong signal, which is then shown in more detail here, is this tyrosine. So that's interesting for us, because tyrosine regulation is often important in endocytic signaling systems. So then we went to check the conservation of these motif signatures, and I will zoom into more detail in a minute. But the top sequence is Homo sapiens, and we have these candidate motifs, which I will go through in a minute. And then we have mammals, we have birds, we have reptiles, bony fish, and then the most primitive or deepest diverged organism in this list, the hagfish, which is a jawless vertebrate, and it has the ACE2 gene and protein, and we haven't been able to find that in any more deeply diverged organism. What is a hagfish? That's a hagfish. Quite common. They don't have jaws. And so 500 million years ago, our ancestors looked like this, and then we diverged from them. Right, let's look at it more deeply then. So we've got 500 million years of conservation of these motifs in these tails. It's one of the nicest alignments of motifs that I've seen. So just wished I'd looked at it a few years earlier. Right, I'm going to go from the C-terms, the back end, and introduce these motifs. The PBM, that's a PDZ binding motif. PDZ domains, quite a large family of domains. So we have many copies. They don't all bind the same sequences. They have very strong preference for the very end of the amino acid chain. And only a few of them recognize a TXF motif with high affinity. So our choice of what might be happening here is limited to a few proteins, and that should be resolvable fairly fast. The next motif I'm going to talk about is this NXXF. You can see a red proline. Proline is not allowed because of backbone hydrogen bonding. Now, the known examples of this is another large domain family. PTB stands for phosphotyrosine binding domain. However, many of them don't bind phosphotyrosines, they bind F or Y, so they're not phosphorylated as well. We don't know, again, which member of that family is going to have the preference in here. Okay, oops, I didn't mean to do that, clicking is a mistake. Right, now, so then I can come over to this rather complicated region where actually we can see 4 motifs superimposed on top of each other. Now the Y is the tyrosine that can be phosphorylated. The only one of these 4 motifs which can be which combine a phosphorylated tyrosine is the SH2 binding motif. So the protein NCK SH2 binding motif has a preference for the kinds of amino acids that are shown here, and the phi is hydrophobic. So it's not an exact residue, but it needs to be a hydrophobic residue. So I'll just go from the top motif there, the I bar motif, this MPY. This MPY motif is known from pathogenic E. coli bacteria, but nobody has ever studied any human proteins with these MPY motifs. The I bar domain it binds to bends membranes. So that's a very practical interaction to have, because you need to bend membranes during endocytosis and other membrane vesicle processes. That MPY is conserved in the hagfish. The reptiles have lost it, but unless you're Harry Potter, you can't ask them why. So, so that's a very nice conserved motif. The endocytic sorting signal is a very simple motif with mainly a Y and a hydrophobic, and it cannot be phosphorylated to bind. But we know already from literature that endocytic sorting signals can switch with SH2 motifs according to phosphorylation. And then the 4th motif is a motif that would dock with proteins that lead to the autophagy systems. And it's known that that SARS and SARS-2 assemble, when they're actually assembling the viruses, they are repurposing, for not entirely clear reasons, autophagy components. So this motif would potentially be able to bring the SARS-2 protein all the way through to the autophagy systems, and then where the process of replication could begin. So all of these motifs need to be verified experimentally. Just finding them in the sequences doesn't mean that they're real. But in particular, if the autophagy motif does bind, then I think this is going to be very interesting, because it opens a path to studying how the virus moves into the autophagy systems. So these are the motifs that we can see in the tail. Right. Now, what about drugging? Well, if we know where we are from by validating, look for targets in the cell that we might be able to hit and therefore slow down the viral infection. Just before I describe these 2 trials, there are tyrosine kinases like ABL and SARC, which are always needed in endocytosis because they control the formation of the actin filaments underneath the membrane. So we would certainly like to see those targeted in various different kinds of infections. Now here are 2 tyrosine kinase drug trials that are starting in the UK for Covid-19. And the first one makes very good sense, because the AXL receptor tyrosine kinase is a suppressor of innate immunity. So if the virus is blocking, or rather activating it, if the virus activates the AXL activity, then innate immunity will be suppressed to the virus advantage. The second example, and I'm not involved in any way, by the way, these are just published on the literature on the internet. So the Bruton tyrosine kinase is an activator of cytokine production. It's basically expressed in white blood cells, and it's particularly the cytokine production in macrophages is an area that they would like to try and target. And in this case, it would be for the late stage of COVID-19 lung disease, where fibrosis is setting in and the cytokine storms are happening. So this would be actually treating the symptom rather than the virus, whereas the first study would be looking directly to drug the cell in order to try to suppress viral replication. Okay, so thanks for listening, and I will try to return the screen now.
Many thanks, Toby. Also to John again. We are still over time, so I can only take one question per speaker. So, John, are you still online?
I think so, although strangely my video is not. Oh, there we go. Everything.
Perfect. So one question is about the relation between SARS-CoV-1 and SARS-CoV-2. The question is, how similar is the spike or the main protease between them?
They are extremely similar. I forget the exact number, but it is, I feel like it's 76%. So there's a lot of similarity. I think many of the structural conclusions, certainly at the level we can currently do structure prediction, are very transferable. That's one of the reasons we weren't even really thinking that much about it. Like the structures that came out really didn't contain a lot of surprises because we knew so much from the previous SARS structures on the spike.
Okay, thanks. There are more questions for you. We will post them online after the webinar. Guido, are you online? Do you want to post your questions directly to Toby?
Yes, I can. Yeah, I was just wondering whether you say that the SLIMs are too short to be identified bioinformatically, but there might be sequence information in the context on the flanking regions. Is that something that could be used to predict them?
So you can attempt to predict them bioinformatically. So Norman Davies' SLIM search tool, for example, is one that could be used. It's just that only looking in the sequence itself is not giving enough information. And they vary in complexity. The ones which have only got 2 conserved or semi-conserved positions, I mean, these are coming up every few hundred residues. Coming then to the topic of the flanking regions, actually the flanking regions are quite interesting. They are often weakly conserved, but they are often involved in the regulation of the, if you like, tuning of the binding affinity of the motifs. So many of them, there's often phosphorylatable residues, for example, which might either increase or decrease the affinity of the interaction. So we can see sort of even rheostatic effects in there. So, but if you do want to try to predict them, then you do need the contextual information. I think there's no other way.
All right, thank you.
Yeah, so thanks to both of the speakers again. And let's move on to the final.
Thank you.
Yeah, so we're moving on to the final section on modeling and tracing, and the speaker is Lenka Zdeborova from CNRS and CAS ACLE, and she's a fellow of ELLIS, but not of the health program, but thanks to these workshop series, she has started to work on health-related topics. So I'm extremely eager to hear what she has to say. Lenka, take it away.
Okay, thank you, Guido. I will try to share the screen as everybody else to go to my slides. Are you seeing my slides?
Yes.
Anybody? Okay, great. So yes, thanks for organizing this, because indeed, I want to tell you about COVID risk estimation from contact tracing data. Something that I have started to work on exactly 5 weeks ago on the evening of the first ELLIS COVID workshop, after reaching out to Joshua Benjo and asking him about what he was talking about in his talk. And after the second ELLIS COVID workshop, I reached to another speaker of that one, Luca Ferretti, who is working on related topics, and we got some really nice realistic contact networks from him, so you will see those. So, okay, so now how do I switch to my next slide? Sorry. Oh, okay, okay, now it's working. So contact tracing data, what the apps that a lot of people are discussing should be collecting is, or storing at the phone, is information about individuals. So this can be their age, their syndromes that they have at any given moment, or other health related risks, such as maybe those that Uri was mentioning. And then the information about contacts between individuals. So that should go to both the phones of both the contacts. And this will include the time at which the contact happened, the duration of the contact, ideally the distance during the contact, and also some information about barrier measures that were used, for instance, if one of the person used a mask or things like that. So the contact tracing that all of you surely read about and heard about as discussed currently is doing the following. It, upon a positive, so it's collecting that information on the phone, and upon a positive test of an individual, his or her recent and sufficiently close and sufficiently long contacts are contacted and either tested or advised to be tested or advised to be self-isolated. That depends on the whole system. So this, how this is working and how this is advantages for the whole epidemic problem. This was something that Luca Ferretti covered at that talk at the second COVID ELLIS. I'm giving you the link to his working paper on this, or with many other authors. So by the way, the slides, they are available on the GitHub webpage that will be linked on several of the slides, so you can get all the links easily from there. So this is something from our rounds, but it's very much in line what Luca was showing in his talk. That's how the contact tracing is advantageous to actually control the epidemic. So what I'm showing you here in the dashed broken black line, that's an uncontrolled epidemic on a graph of, here it is 10,000 individuals, on the right you have the set of parameters. So that's completely uncontrolled epidemic. The blue line, that's an epidemic where I randomly test individuals. I also test half of the symptomatic cases, and those cases that I found positive, I set them into quarantine. I isolate them from the rest of the network. So if I do that isolation, then I flatten the peak and lower the peak and flatten the curve. And then the orange curve, that's the result of the contact tracing, where instead of the additional tests to the symptomatic ones, instead of doing them at random, I do them based on the contact tracing. So who was the one that was most often in contact with people that before were tested infected? So that's the effect on the epidemics. It's, this is some example, but it can have a big effect. It can completely flatten the curve just by doing that. And so can we do better than just the tracing? So at which point better? So we call that the smart inference of people at risk. So there is much more information in this data that the app is collecting than just the list of contacts. You should actually take into account the fact that individuals, their risk is given also by, it doesn't have to be that one of their neighbors was tested positive, but if everybody is computing their risks, then the increased risks of their neighbors is increasing their own risks. So this should be self-consistently taken into account. And this is what we are doing, what I will be telling you about. And what is needed from the app on top of what they are already planning to do or doing most of them is simply communication between the individuals who have been in contact. So this can be done at the moment of the contact with some broad, with some low bandwidth, in some low bandwidth manner via the Bluetooth, for instance, before connecting actually the Bluetooth to each other. Or it can be done later after the contact through some encrypted communication through a server. And again, only a very small bandwidth is needed to do that. So this should not be overloading the network. So as far as we found out or know, there are many of the apps currently being developed, but only 2 of them were actually, as far as we know, they are trying to estimate the risks in a more advanced manner than just who has been in contact with somebody who tested positive. And this is on the one hand exactly what Joshua Benja was talking about, so the app being developed in Canada by his team, and another one called ViaTrace that is being deployed in India. So in our work, kind of where we position ourselves is to provide and test and validate the algorithm to actually estimate those risks. So we work with 3 algorithmic approaches. One of them, the simplest one, the mean field risk estimation, I will describe. And the other one, I will tell how they differ after I describe the simplest one. So here I just remind you the SIR model for epidemic spreading that by now, you know, all of you have heard about for sure. Here by the SIR model, I am not meaning really the one differential equation that describes the whole population at once. We use it at the level of the individuals and the contact network between them. So every individual has a state, and what is crucial here is the crucial parameters here is the lambda ij as a of the time, which is the time dependent attack rate, which is a probability that if node J was infected, that at time t, it would actually infect node I if they were in contact. And the value of this lambda J is actually estimated from the duration and the distance of the contact and the barrier measures. And the other parameter in the model is the recovery rate. So that is when you are infected, what is the probability that you turned to recovered? And then what we are interested in is actually the probability of a person to be in one of these three states. And we will denote those for person I, the P of S, being susceptible, infected, or removed, recovered at time t. Oh, sorry, I move that, and now I don't know how to go to my next slide. Why is this not working? Okay, that's the next slide, great. So if we knew these probabilities at time t, then a pretty intuitive way to recompute them at the next time is the following. So the probability to stay susceptible will be the probability that I was susceptible at the previous time step minus sum over all the contacts I had at that time of what? Of the probability that I was susceptible, that I met my contact was infected, and times this attack rate, that is the probability that the infection was passed. The second equation, how does the probability of being recovered evolve, is simply the probability that I was recovered before, so I only stay recovered, and I add the mu times the probability that I was infected. And the third equation is simply, you know, these probabilities must add up to 1, so I take 1 minus the first minus the second. And these are pretty intuitive. What they do not include yet, and when there is the most information kind of in this contact tracing, is actually the results of the tests or eventually the symptoms. So to take the tests into account, we implement the following feedback loop. So this slide is a little bit busy, but if you go to the links there, you can sit with it in calmly. But what it does is that the moment somebody tests infected, we estimate this person was already infected for tau steps before that. And so we go back those tau steps and set the probability of that person being infected to 1, and then rerun the message passing forward in time to the present time. And this takes into account properly the fact that somebody was infected. Okay, I should really not be moving my ball because now I don't know how to go to the next slide again. Okay, I don't know how this works. Okay, sorry for that. So here, you know, just to say how these two other algorithmic approaches that we are using differ from that. So the dynamical message passing does somewhat fewer approximations than what I have shown you is doing. And the third approach, the belief propagation of our collaborators from Torino, is actually looking at the probabilistic model that properly conditions to the dynamics to the observations. So this feedback loop is much less ad hoc in that approach. And these are actually approaches that, you know, both the collaborators from Torino and us have worked on, say, 5 years ago. And back then, kind of the referees were saying, yeah, but you don't have the contact network. And you were saying, yeah, we know, but it's still interesting. But now, I mean, we can, you know, at least locally, the phones could have the contact. So here I start to show some results of that. So this is just the sanity check that the probability estimation we are, you know, computing actually agrees with what would have been happening if you ran the dynamics, the SIR dynamics many times. And being on the straight X line means that it works. So this would be without the feedback loop, because without the feedback loop, we can easily do the Monte Carlo dynamics and check. So this is just saying, it works. And here I'm showing you some of the, in epidemiology, the ROC curves are often used. So what these curves are is that when you have a method to estimate the probability of a risk of somebody, then you rank those probabilities, start with the highest one, and if it is a true positive, you go up, and if it is a false positive, you go to the right, and then you go on until you exhaust your whole population. And if your ranking was just random, you will do some random walk like the blue line in this figure. So this is not very good. But if you rank using the tracing, which is the orange line, you will do, you will be higher, and higher is better. And if you rank using our approach, you are even higher. And this is, for instance, on a graph that is, that was provided to us by Luca Ferretti, that comes from Dermal, run by Rob Hinch, and that I referenced previously. So now the same graph on a slightly different network, but still provided from that realistic epidemiologic model by Hinch et al., where now I compare to the approach of our collaborators from Torino, so Brownstein et al. And I link here their GitHub notebooks where you can reproduce all those graphs. You can directly go to the notebooks and see how exactly they were obtained. To show you there is additional space for improvement if you use their approach. So that's the orange curve that is even higher. So this is really exciting. This seems to be quite powerful method. And it's slightly more expensive in terms of the bandwidth that you need to send the messages between the phones, but it's a kind of trade-off that we need to explore, like whether the gain is big enough for this to be worthy eventually. And on this slide, I am showing you, this is the figure that I have already shown at the beginning when I was explaining that tracing is flattening the curve and moving the peak. And here I added the green curve, which is what happens if we actually rank not according to the tracing, but according to our method. So you see that the peak is lowered and the epidemic basically is completely diminished much before it would be if you were not doing tracing at all, and also even better than if you are just doing the naive contact tracing where you just contact the people that were in contact with somebody infected. And this is the same thing on now this is supposed to be a video. Yeah, that works. So this is the same kind of a control of the epidemic on, again, one of relatively big graphs. So this is 50,000 individuals from the model that is from the epidemiologic model by Hinch and Ferretti. And here I am showing you what happens if you are testing more and more individuals. So here I'm testing half of the infected people. I assume those have symptoms serious enough that they actually go to have a test. And additionally to that, I test a given number, so 50, 100, 200, or 400 of individuals according to the ranking. So the black curve is the uncontrolled epidemic. That's there for comparison. The green is if the ranking, the blue is if the ranking is random. So you see that it's going down if I test more and more, but kind of, it just exploits what is there in the information that is there in the additional several hundred tests. But the contact tracing is going down faster as I am using more and more tests. And the mean field estimation of the risk is going down even faster. So here we are seeing that with sufficiently many tests, we can diminish the epidemics much faster. So what sufficiently many means in practice, we would have to go, to population sizes and even more realistic kind of parameters. So that's basically on my next slide. What we are working on right now is going to larger networks so that we can look at yet more realistic epidemic spreading models that, where really few individuals are actually infected, networks of millions of nodes, next thing we didn't yet implement this this control of the epidemic together with the Brownstein belief propagation algorithm that was doing the best on the ROC curve comparisons. So we are really excited and waiting to get that. We need to explore the role of the various parameters, because I was showing you those graphs and not really going into the detail of all those parameters that were listed there. But it's of course, there are several of them. It's of course important to know their role and include more info from the simulator, because the simulator, for instance, includes age groups and who is living in the same household and details about the syndromes that we are not so far included in the inference model. So this would provide additional information and additional kind of performance and prediction and performance. And we also kind of need to be learning the parameters. So far, we are doing it a bit by hand, trying a number of them. And that also goes to my last slide now, like what's next. So actually going back to what Joshua Benja was telling us 5 weeks ago, and I have been following their progress at the Mila, you actually can learn not only the parameters of the common SIR model, but you actually could think about learning the whole model in a very much AI, a modern machine learning, deep learning way using graph neural networks. And interestingly, it's something that just a few days ago, Max Welling was also posting about on Facebook for people who are interested in that. Next thing that also needs to be done is that so far we were assuming the contact network is known perfectly. But if we want to implement the app in a privacy preserving way, then the contact network will not be known perfectly. So including that into the implementation is an important kind of factor and needs to be understood and tested. So let me know if you want to work with us. All that I have been telling you about, you can read about it at the Git repository and try those notebooks, or on the overleaf where are our notes. And I guess that brings us to the question time.
Thank you very much, Lenka. As has been the case for all of these workshops, we are greatly over time, unfortunately, so there's time only for one question, and there's a question from the audience, which is, you're using SIR dynamics, but many people argue that an SEIR, so where there is an exposed but not yet infective period, is a more accurate description, which would introduce a delay in the dynamics. How would your contact tracing model apply to this situation?
Yeah, so actually the model that is doing the dynamics, so there are two kind of ways in which I'm using the SIR. One is, what is the model that is spreading the dynamics? And for this, we are using the model that Luca was describing, and that one is even more complicated. It has a lot more details. It has not only 5 states, but more states for the different kinds of syndromatic people. So we are kind of happy about that, because for us it's kind of the real world. We don't really know what the true model is, and it's more complicated than the model that we actually use for the inference. And of like usually machine learning, right? When you do linear regression, you assume that your data lie on a line. So even when they don't lie on a line, then we validate it on the ground truth, how well does it do. So we could also include the E state in the inference. The question is, would it actually bring some performance? Maybe. I mean, it's something that is somewhere on our to-do list. We are somehow bringing it in the fact that the symptomatic people that are being tested, the way we actually model who's being tested, for everybody who is infected, we wait for tau days before actually including them in that group that is being tested. So that's a little bit like the exposed but not yet symptomatic state.
I see. Thank you very much. So thank Lenka, thank all the speakers for this workshop, which has been very exciting as all the other workshops. So there is not much time left for the global discussion, but let me reiterate, it will be another workshop scheduled for the 20th of May. And we are always interested to hear from people that are doing work on COVID that want to present. If you are doing work on COVID and would like to present, get in touch with Daniela, who's our main organizer, and she can be contacted at the COVID-19 at ELLIS address. So thank you very much to everyone and have a pleasant rest of the day.
I'll stop sharing.
Bye now.
Thank you. Goodbye.